Welcome back, everyone, for another deep dive into the OEIS.
It's great to be back.
Today, we're going to be looking at a pretty cool sequence.
Yeah, this one is quite interesting.
It's a 000180.
A classic.
The title that the OEIS gives it is Expansion of E.G.G.F. And they write it out like that exponent of x over 1 minus 3x.
Right.
Now, just as a reminder for our listeners, A.G.G.F. stands for exponential generating function.
Exactly.
So basically what we're saying is this sequence comes from the power series expansion of this particular function. And to give everyone a sense of what this sequence looks like, the first few terms, and I'll start at n equals 0.
Okay.
We've got 1, 2, 13, 1, 16, 1,393, 20,894, 376,093.
Wow, those numbers get big fast.
They really do. And, it just makes you wonder what kind of underlying structure could be generating a sequence like this.
Yeah, and I think a big clue is that exponential generating function part. That kind of hints that maybe we're dealing with something involving factorials or exponentials, things that grow really quickly.
I see.
Which would make sense given how fast those terms are increasing.
That's a good point. And what's so cool about the OEIS is that it doesn't just give us one way to define the sequence.
Right.
It often gives us like a whole bunch of different ways to think about it.
Exactly, and that's what makes it such a rich resource.
So beyond that exponential generating function, what are some other ways that we can define and understand A000180?
Well, one way is using a summation formula.
Okay.
And this one is credited to Cloitre.
Okay.
And it says that the nth term, which we can call a of n, is equal to the sum from k equals 0 to n of negative 1 to the n plus k times n choose k.
Right.
Times k factorial times 3 to the k.
Wow, that's a mouthful.
Yeah, there's a lot going on in that formula.
Yeah, there is. We've got alternating signs. We've got combinations, n choose k. We've got those factorials and then powers of 3.
Yeah, there's a lot to unpack.
It is. What kind of combinatorial situation could lead to a formula like that?
Well, one thing that jumps out at me are those alternating signs.
Okay.
Whenever you see that, it often means you're dealing with some kind of inclusion-exclusion principle.
Right, where you're counting things and then you have to subtract away some stuff that you've overcounted.
Exactly, and then you might have to add some stuff back in that you've undercounted and so on.
Okay, I see.
And then the binomial coefficient n choose k that suggests that maybe we're choosing some objects out of a set.
Like we've got n objects and we're picking k of them.
Exactly, and then the k factorial might be permuting those k objects in some way.
Interesting.
And the powers of 3, well, those could represent choices that we're making at each step.
Like at each step, we've got 3 options.
Right, or maybe it's some kind of weighting factor.
So even though we don't know exactly what kind of objects this formula is counting, it seems like it's describing some pretty intricate counting process.
Absolutely. It's a counting process with lots of little twists and turns.
I like it. Now, the OEIS also gives us another really cool way to approximate the terms of this sequence.
Oh, yeah. Tell me about that one.
It says that a of n is approximately equal to 3 to the n times n factorial divided by e to the 1/3.
That's interesting.
And then you take the nearest integer to that.
So we're connecting our integer sequence to this irrational number e.
Yeah. It's pretty wild, right?
It is. What's the intuition behind that?
I don't know. What do you think?
Well, when I see approximations involving factorials and exponentials, it often makes me think of asymptotic analysis or maybe probabilistic models. Like maybe there's some quantity that's very close to 3 to the n times n factorial divided by e to the 1/3. And our integer sequence is just the result of rounding that quantity to the nearest integer.
So it's like the integer sequence is shadowing this continuous function that involves e.
Yeah, that's a good way to think about it.
Now, moving on, the OEIS also mentions some recurrence relations for this sequence.
Right, recurrence relations are super useful.
They are because they tell us how to get the next term in the sequence based on the previous terms.
Exactly.
And R.J.Mathar conjectured a 3-term linear recurrence.
Okay.
But there are other forms, too.
Like maybe simpler ones?
Yeah. For example, Riordan gave us a 2-term linear recurrence.
Nice.
It says that a of n plus 1 is equal to 3n plus 2 times of n plus 3n times a of n minus 1.
I see.
And the initial condition is a of 0 equals 1.
So we can just plug in the numbers and crank out the terms.
Exactly. It's like a recipe for the sequence.
It is, and this kind of recurrence often means that the objects we're counting can be built up recursively.
Like we can take smaller objects and combine them to make bigger ones.
Exactly.
And Werner Schulte gave us another recurrence.
Okay, what's that one?
It says that a of n equals 3n times a of n minus 1 plus negative 1 to the n.
Oh, I see. So we've got that alternating sign back again.
Yeah, it's like we're adding or subtracting something depending on whether n is even or odd.
Right, like we're switching between two different cases.
Exactly. And, you know, it's amazing how many different relationships these terms satisfy.
It really is.
We even have a connection back to the exponential generating function through a differential equation.
Oh, wow.
Cloitre-style pointed this out.
What's the equation?
It says that 1 minus 3x times a prime minus 2 plus 3x times a equals 0.
Okay, so a is our exponential generating function.
Right, and a prime is its derivative.
Yeah.
And this is a first-order linear differential equation.
So we're connecting generating functions to differential equations.
Yeah, it's like we're bridging the gap between continuous and discrete math.
That's cool.
Yeah.
How does this differential equation help us understand the sequence?
Well, the key is that the coefficients of the differential equation are related to the recurrence relations for the coefficients of the power series.
Oh, I see.
And those coefficients are the terms of our sequence.
Right.
So if we were to take our exponential generating function and write it out as a power series, and then substitute that into the differential equation, we could actually derive the recurrence relation for the terms.
So the differential equation is like a compact way to encode the recurrence.
Exactly.
That's pretty neat.
It is. Now, for our listeners who want to delve even deeper into this sequence, the OEIS entry lists some great references.
Like what?
Well, there's Riordan's book, An Introduction to Combinatorial Analysis.
Oh, classic.
And Sloan's books, A Handbook of Integer Sequences, and the Encyclopedia of Integer Sequences.
Those are foundational works.
They are, and they provide a lot of the theoretical background that you need to really understand these kinds of sequences.
Oh, really?
And the OEIS page also lists some related sequences.
Okay, like what?
Well, there's column K equals 3 of A320032.
Interesting.
And then there are adjacent entries like A0000177 through A0000179 and A000181 through A000183.
Right, those are like its neighbors in the OEIS.
Exactly. And exploring those connections can give you a much richer understanding of what's going on.
It's like looking at the bigger picture.
It is. So to wrap things up, we've seen that A000180, which is defined by this exponential generating function,
Exponents negative x over 1 minus 3x.
Can also be expressed in a bunch of other ways.
Right.
We've got a summation formula involving binomial coefficients and factorials, an approximation using E, multiple recurrence relations, and a differential equation for its generating function.
It's amazing how much information is packed into this one sequence.
It really is, and it just shows how interconnected different areas of math can be.
Absolutely.
So for you, our listener, we'll leave you with this final thought.
Okay, hit me.
What fundamental principles might be connecting all of these different representations of A000180?
That's a great question.
And how do those principles relate to the connections that we see with other integer sequences in the OEIS?
Lots to ponder there.
There is. Thanks for joining us on this deep dive into A000180.